This is the story of a new world. A world that begins in the mysterious and invisible universe of atoms and molecules, which combine in countless numbers to form everything we see and touch. It is the story of how man, investigating nature, has learned from nature's examples to join these same atoms and molecules to form substances never before seen under the sun. These new materials are the world of plastics, the world that nature forgot. The story of plastics may begin with something as familiar and as wonderful as a phonograph record. But it is a story that has no end, for the future of the world of plastics is far beyond the vision of man, and still hidden in the world that nature forgot. In the world of nature, air is the breath of life, sweeping gently and sometimes harshly over the weathered face of the land. Air and water, undulating ceaselessly to form the ever-changing and changeless face of the sea, warming and evaporating to rise in the air, to be borne by air in graying clouds, often for thousands of miles, only to fall again to nourish the land with gentle rain. And afterward, in ever-growing torrents, the waters return to the sea once more. The world of nature needs air and water, and it needs the minerals of the earth, which air and water slowly leach away from its ageless crust. Plants need all these things: air, water, minerals from the earth. They need the energy of the fiery sun. To gather water and minerals, they send roots deep into the ground. From the tap roots, branches spring out to search the soil and absorb its nourishment. And as the plant draws strength from the earth, it breaks the surface and feels for the first time the light of day. As it grows, a plant spreads its leaves to take in air and absorb sunlight. Through tiny veins in the stem of the plant, water and minerals gathered by the probing roots flow upward to the leaves and are carried by other veins out into the leaf cells. Through dark-rimmed pores in the leaf, the plant draws in carbon dioxide from the air, which meets with the water and minerals in other leaf cells. Using energy from the sun, the plant synthesizes these molecules into ever longer ones, strands which form the fabric of bark and leaves and cells. Thus, from the inanimate crust of the earth comes the living world of nature. And from the world of nature comes the world of man, who has built his homes with the great trees of the forests. Man has taken the very fibers of nature, like those of cotton, and learned to weave them for his comfort. Digging deep into the crust of the earth, he has found metals for tall buildings and long bridges, and minerals like sand for the windows of his homes. In mills that stretch across the land, he forms and fashions and molds nature to his purposes. And in nature, he found the power for these factories, the power of long dams that interrupt the waters as they rush to return to the sea, dams that exploit the descent of the waters to turn turbines and generate electricity for the dynamos of the city. From all these elements of nature, man has built his cities and his civilization. And in building his world, man has found a completely new power, the power of gleaming chemical plants, which, like the growing plants of the fields, take in nature's simple molecules and change them into new molecules, which form substances never before seen under the sun. These new materials constitute the world of plastics, a world which begins, like the world of nature, with air drawn into great ducts and passed through a maze of pipes. And the world of plastics takes water, used as steam and then condensed in massive cooling towers to fall like rain and nourish the plant again. And it takes fire instead of the sun to forge new molecules from air and water and chemicals. Chemicals which are drawn from the earth and stored and have names like benzene, methane, and propane. Abstract patterns in pipe, like the delicate veins in the leaf of a plant, bring the materials together. Red and yellow pipes for chemicals. Aluminum for steam. Dozens of high-speed pumps and compressors move them at the right time and the right speed. Monitoring the whole plant are men, ever watchful men, who make their rounds to take samples of the molecules forged in fire, and to watch the instruments which read the pulse of the plant. And finally, it takes the towers, tall towers that reach up to the sky to distill the basic molecules from which plastics are made. Substances that are shipped out in tank cars and bear names like styrene, vinyl chloride, acrylonitrile, simple molecules that must now be linked to form the fibers of a solid substance. Unloaded at the processing plant, the materials are piped into storage tanks. Then they enter the plant and are piped into kettles, where under heat and pressure, the simple molecules link together to form the long strands of a plastic material. Some plastics, like phenolics, flow from kettles as a thick liquid, which is allowed to harden. Then they can be reheated to form TV cabinets, telephones, or the nose of an anti-aircraft shell. Others, like vinyl, emerge as tiny grains to be dried in heated cylinders. Heavy hammers jaw loose the powder that sticks to the walls within. Once dried, the powder goes to a screener. Flowing from the screener, the vinyl may be used to make raincoats or shower curtains. Styrene, mixed with colorants in a blender, can be given every color of the rainbow. The mixture passes downward to a heated cylinder, where plastic and colorant melt together. Forced from the cylinder through a series of openings, the styrene emerges in thin rods which pass through water, cool, and solidify again. The rods are chopped into colored pellets, which the manufacturer can melt and mold to form modeled trains or phonograph records. So new and unexplored is the world of plastics that its future and its possibilities are only vague and colorful forms in the minds of men. The materials can have an infinite variety of color and shape, and for each a use. But only the coast of this new world has been touched. The rest is uncharted, and so filled with promise that no man dare predict what will be found there. Today, the artisans and architects of that world are just beginning to mix their paints, and the picture that will finally emerge has barely been started. A world in the making, all achieved by linking together a few simple molecules. A few simple molecules made from hazy, even simpler atoms. Atoms that move endlessly. Carbon atoms and pairs of hydrogen atoms. Simple ingredients for a world as lovely as the world of nature. Simple ingredients for a world as promising as the world of plastics. One of the most basic molecules is ethylene, formed from hydrogen and carbon. Ethylene is the basis of many other plastics, a molecule which in other industries is used to make alcohols and other chemicals. In the plastics industry, ethylene molecules are heated, move faster, and fuse together, forming the long strands of the plastic polyethylene, which is used for squeeze bottles. When pairs of chlorine atoms react with ethylene molecules, a new substance is formed, vinyl chloride. And as these molecules form chains, they give another plastic, polyvinyl chloride. A brittle material, vinyl becomes a useful plastic when a substance called a plasticizer is added. Slipping between the long strands, the plasticizer acts as a lubricant, allowing the molecules to slide over one another and form a flexible material. Another common chemical is benzene. When benzene reacts with basic ethylene, the result is styrene, a clear liquid used in making synthetic rubber. And when styrene molecules join, they form polystyrene, one of the most versatile plastics, useful for housewares, toys, and radio cabinets. A few simple atoms, a little heat, an endless amount of research, an inexhaustible variety of different plastics, and a brand new world. The final forming of almost any plastic requires heat and pressure. But depending on the plastic, the way these are applied will differ. One such process is calendering. Vinyl is hard until mixed with a plasticizer, which makes it mixable. Hitting the hot mixing rollers, it turns to gum and is kneaded like dough. The thick strip first formed passes to other rollers, which press it into an ever thinner and ever wider sheet. Finally, the thin vinyl film is rolled up like ordinary cloth for raincoats, wall covering, and upholstery. This process may one day yield a continuous ribbon of highway material. Heat and pressure are also used for injection molding, by which such products as refrigerated door panels are formed. Once the panel has been removed, the halves of the mold close again, and the plunger forces more hot styrene into the mold. Injection molding is indispensable for industrial items like air conditioning grids and acid-holding battery cases formed of inert styrene. A multitude of other items flows from compression molding, in which materials like phenolics are melted and pressed into form as the hot mold closes. From such plastics come light and durable radio cabinets, or the noses of anti-aircraft shells, or washing machine agitators that must withstand the heavy wetness of clothes. In vacuum forming, the molds are perforated by tiny holes, and a vacuum is applied from beneath. The heat of an electric grid softens the sheet of styrene, and the vacuum draws it over the mold to form funnels. Used on a larger scale, vacuum forming may one day produce whole sections of automobiles. Foamed plastic is one of the newest in a family known as urethanes, foam which can be as rigid as plywood or as soft as a pillow. Unlike most plastics, urethanes require no external heat to set, but foam as they are mixed and poured. When the basic chemicals flow onto a moving form for actual production, the urethane swells and whitens into foam. This foam can be used for fire-resistant and weight-saving cushions for airplanes. In solid form, urethanes may one day yield 100,000-mile automobile tires. Versatile in themselves, plastics are also invaluable in combination with other materials, such as glass fiber, which can be shredded and sprinkled over a mold to form a crude mat. The mat is welded together into a solid mass when a polyester plastic flows among the fibers and hardens under pressure to hold the fibers fast. The result? A finely formed salad bowl. Such reinforced plastics can also form car bodies or swimming pools. Because plastics can hold flexible materials in a rigid shape, they can form durable laminates. Such laminates, called sandwiches, can begin with a sheet of plastic laid in a mold. The strength of the sandwich comes from strips of pliable honeycomb material. A final layer completes the laminate. Heat will weld it to the honeycomb and hold it in a rigid shape. These inexpensive laminates are now being used for many airplane and ship components. Even paper or a veneer of beautiful wood can form a tough laminate when impregnated with melamine and drawn upward through a dryer. The surface layers of these laminates can be colorful and can be printed in patterns. To hold the visible surface sheets, impregnated undersheets are stacked up like cards and the surface sheet laid on top of them. A polished mirror will impart its smooth finish to the sandwich. Once it has been heated in an oven and the plastic melts to fuse the layers together, forming a laminated tabletop or wall paneling. So strong are the adhesive qualities of plastics that they can weld together long planks into beams of a size never contemplated, giving wood a versatility it never had before. Such beams built up from layers of welded wood can form the vault of a church or great arches to support a bridge. Clamped together, the planks are grasped by the plastic, and only disintegration of the wood can separate them again. Here again, plastics become a partner of another material, in this case giving new strength to one of the oldest of all materials, wood. Durable monuments for the enduring works of man. In a world as flexible as the world of plastics, the durability is easily translated into a transparent film like polyethylene. Tough and inert, polyethylene can be extruded as a continuous thick coating for an Atlantic cable. Extruded as a thin film, it can form moisture-retaining vegetable bags. Stretched and cooled, the film is wound on a drum to be cut into bags by the manufacturer. Like polyethylene, acrylic fibers such as acrylan are extruded. They emerge as clean white filaments. Wet from the bath in which the plastic has solidified, the filaments must first be stretched and dried. Gathered together and crimped to give them the crinkles of natural fiber, the filaments move on through guides and rollers. A clean white, they can be dyed any color. Then the fibers descend like a downward rushing river to be chopped into short pieces. Afterward, they are rolled into fine, light, fluffy lengths, a material which now must be twisted and tightened to form a tough yarn. Wound on bobbins, the yarn is then woven into cloth. Though light in weight, synthetic fibers can have the tensile strength of steel, a strength that can be demonstrated in the laboratory. Looped about a steel couple, a nylon filament draws upward against the resistance of a steel wire of equal thickness. Thread and wire grow thin with tension. And suddenly, the graft drops to zero. The steel wire has broken, and the couple swings from the nylon thread. Toughness is also important in a plastic that forms the meat of the safety glass sandwich for a car's windshield or window. While some materials must withstand a moment of shock, others must be prepared for the constant attrition of more leisurely movement. Many plastics are excellent insulators, but only prolonged high-voltage tests can reveal their resistance. Plastics can be molded under a variety of temperatures and pressures, but under some conditions they develop unseen, produce stress-free products. Colors seen under polarized light may see the light of day. When in paint, they are subjected to the rigid test of exposure to the elements. Today, plastics are an integral part of most paints and surface coatings. These are the acid tests of a vision of a world of plastics. A world that has already penetrated every home in the land. Today, we can see a part of this world in beautiful draperies, in stainless tabletops that are so useful they are commonplace, in radios, in durable floor tiles, or a refrigerator that is clean and neat and colorful. The new materials protect a man's clothing when he is home, and they can also guard it when he travels. In the household of today, they are present everywhere, preserving man's memory of nature in panels of wood, preserving his memory of himself and his desires and his hopes in the fine grooves of a phonograph record. And as a man works, they surround him like the servants of another age. The world of plastics is present everywhere. Yet this presence is but a premonition of a future world. Our children will see a bit of that world, and our grandchildren will not see the end of it. A part of the home, plastics are also a part of the world of the scientists and engineers who think about the other side of tomorrow. Injected into a heart, a liquid plastic fills the myriad vessels which nourish it. And after the tissue has been dissolved away, the plastic furnishes a complete map of that great organ's circulation. In the strange and vital field of atomic energy, the new materials protect scientists from the danger of deadly radioactive dust. Dust generated by the experiments carried out in sealed rooms, which nevertheless must be entered to determine the results of the experiment. And engineers who dream of cars and turbines to power them instinctively think of plastics for their bodies. And even when man ventures under the sea, these materials go with him, forming today the shell of a two-man submarine, and tomorrow possibly the body of a storm-free undersea ship. Such things can only suggest the future. It has taken thousands of years to learn how to handle wood, copper, and iron. And now there are new materials which never before existed, whose names, styrene, vinyl, polyethylene, are still unfamiliar. All of them will help build the city of tomorrow. Lacking 1,000 years' experience, we do not know what form this city will take. For who can foretell a future dominated by the inquisitive spirit of man? Yet like every city man ever built, it will be a city of nature shaped by man. A city of wood and stone and steel and concrete. But in addition, it will be a city transformed by man and his chemistry, and by the new materials that flow from the plants with the tall towers and the colorful pipes. A city built from the world that nature forgot.